on purpose to build some kind of quantum computer. So the idea is, as I said before, it's a cold atoms lab, so we want to use ultra cold atoms, and you want to build a quantum computer. So you have some ingredients, which is a qubit. You have to realize a qubit. You have to be able to manipulate this, to do Hadamard gates, and you have to come up with some idea to create entanglement in the system. And we have some ideas how to approach this in the context of cold atom physics. So all these optics here are meant to cool down the atoms to very low temperatures, a few microkelvin, and then we want to trap them in a magnetic structure, and this structure we call microstructure. Maybe I can show this. So we kind of pattern a permanent magnetic material, and this leads to a potential landscape which can trap atoms, several hundred atoms in one cloud, and these atoms are supposed to be our qubit. And here you can see how this is an old version, how such a chip looks like. So we're trapping the atoms very close to the surface, a few microns, and then we want to manipulate them with light. That's our approach. So I would like to show you the other lab, so where all the light is prepared to do the manipulation of the qubit and to create entanglement. And so this complete optical table is just solely dedicated at manipulating qubits and creating entanglement. So it really, you see that it has a certain complexity. So our approach to create qubits is to encode it in terms of hyperfine structure of atoms, and this table is just dedicated to bring it from one hyperfine ground state to the other, which would be something similar to a Hadamard gate. And then if you pulse your light in a certain way, you can create pi over 2 pulses, pi pulses, and so forth. And another main ingredient was the entanglement. And our way to create entanglement is by involving something which is called Rydberg atoms. So Rydberg atoms are atoms which are excited to very high-lying states. So they are very sensitive to their environment. And you can, the idea is that two atoms in a Rydberg state, they can kind of block each other, prevent each other from being excited. And if you do this properly, you can actually create, you can have two atoms, and if they block each other, they can actually create an entangled object. This is would kind of build this CNOT gate. And in order to do so, we involve a lot of lasers. We involve an infrared laser, a blue laser. We need to pulse them. We need to stabilize them in frequency and phase. And this is what the whole optical table serves. So in the end, we're going to have a combination of optical qubit rotations and an optical way to create entanglement. And by this, we're going to hope to achieve these things soon in our setup.
Nice. Is it nice research to do?
It is indeed, yeah.
Why?
Well, it's very demanding on the technical side. So that's, well, you kind of, you build these things that takes years, but it's definitely a field you learn a lot, and you have a very interesting objects. They are very pure quantum mechanical objects. Yeah, so you can actually really see all these quantum mechanical effects, which seems so weird, but you really see them in practice. So that's quite nice. And I hope at some point, if we achieve these kind of things, then I think it will be quite giving. Yeah.
Right. Thanks.